Good. Hello students. Today we are starting with the new chapter, that is equilibrium of coplanar forces. Now, if there is a body or a particle which is under the influence of forces and we say that it is in equilibrium, the very first thing what comes to my mind, that body is at rest. Little more I think, then it comes to my mind that resultant of all forces acting on it must be zero. That means all forces acting on it are balanced. That is what we can say, that if the body or particle is under the influence of forces is in equilibrium, that means it is under the action of balanced forces. That means resultant of all the forces acting on it should be completely zero. Now, what are the examples? For examples, what are the examples of equilibrium? Like building under the influence of various forces acting on it, bridges, lamp hanging from the ceiling, or a man sitting on the chair. Now, next we understand types of equilibrium. Three types of the equilibrium students we come across. One is stable, unstable, and neutral equilibrium. Types of equilibrium have nothing much to do with the solution of the problems of equilibrium, but still we need to understand different types of the equilibrium. Can you see that on this side? There are three balls kept on three different types of the surface. This surface is with concavity upwards. This is with convexity upwards. This is truly horizontal. Three identical balls are kept on three different surfaces. Small force is applied on each ball so that the ball is displaced from its original position of equilibrium, and then force is removed. Now, what happens to the ball? In the first case, when the ball is displaced from its original position of equilibrium by applying the force, and then the force is removed, the ball comes back to its original position of equilibrium. Such equilibrium is called as stable equilibrium. Next, in this type of surface, then the ball is kept on the surface which is having convexity on the top. If slight disturbance is caused in the position of the ball by applying a force, and when the force is removed, the ball does not come back to its original position of equilibrium. Rather, it goes away. This is called as unstable equilibrium. Now we come to the third case, in which the ball is kept on the truly horizontal surface. A small force is applied on it. The ball gets displaced from its original position of equilibrium. Then the force is removed, but the ball does not come back to its original position. It does not go even away also. So such equilibrium is called as neutral equilibrium. All the engineering structures, what the engineers design, should be in stable equilibrium. Should be in stable equilibrium. Students, in the chapter of resultant of coplanar forces, we had understood that there are three types of the problems: resultant of concurrent force system, resultant of parallel force system, and resultant of general force system. Identically, here also you'll have three types of the problems. One is equilibrium of concurrent force system, equilibrium of parallel force system, equilibrium of general force system. So first we understand what will be the equilibrium conditions for concurrent force system. Concurrent force system will be in equilibrium, when it is completely at rest. Forces are balanced. That means resultant of the forces acting on that should be zero. So resultant of concurrent force system will be zero only when sigma fx and sigma fi both are zero. What do you mean by sigma fx? Algebraic sum of the component all forces in x direction. What is sigma fi? Algebraic sum of the component all forces in y direction. This is, as you can see, that I have listed it as set 1. Apart from that, in the book, when you refer it, my book of mechanics, you'll find there is set 2 also, but which I'm not discussing right now, because at the early level learning, you should not get involved with more sets. This set of the equilibrium condition does not have any limitation, right? So to begin with, we will use only this set of equilibrium conditions for solving the problems. Now, we come to what are the equilibrium conditions for parallel force system. In case of the parallel force system, there will be two equilibrium conditions will be there. One is sigma f is equal to 0 and another sigma m is equal to 0. What is sigma f is equal to 0? That is algebraic sum of the forces acting on the body should be 0, and all forces will be summed up in the direction of action, in which all the forces are acting. Suppose all forces are acting in x direction, so we will use sigma fx equal to 0. Suppose all forces are in y direction, we will say sigma fy is equal to 0. Next is sigma ma is equal to 0. Sigma ma means what? Algebraic sum of the moment of all forces about any point A is 0. Again, student, let me tell you that this set of equilibrium condition does not have any limitation, right? Other set of equilibrium condition is also listed in my book, right, which we use it at the later stage. We'll discuss it at that time. Right now, we will very much stick to the first set of equilibrium conditions for concurrent, parallel, as well as general, because the first set of the equilibrium condition, which I'm showing you right now on the PPT, this does not have any limitation. Now, next we come to equilibrium conditions for general force system. What is general force system? Known concurrent, known parallel force system is called as general force system. This set of the equilibrium condition has been derived by putting the resultant completely 0. Sigma fx is equal to 0 and sigma fy is equal to 0 will ensure that resultant force of the system is 0. Sigma ma is equal to 0 will ensure that resultant moment is also 0. Now, with the usual notation, sigma fx is algebraic sum of the component of all forces in x direction. Sigma fi algebraic sum of the component of all forces in y direction. Sigma ma algebraic sum of the movement of all forces of the system about any point A. A means it can be any point in the plane. Next, we will understand different types of supports. Students, primarily we come across three types of the supports. First support is hinge support. What is hinge support? Hinge allows the body to rotate, hinge allows the rotation of the body, but it does not allow the body to move in x and y directions. As rotation of the body about the hinge is permitted, there is no movement reaction, but the movement of the body is restricted in two mutually perpendicular directions, say x and y. So two normal reactions are exerted by the hinge. So we need to remember that hinge exerts two reactions. As you can see over here, now this is the body, which is, this is the notation for the hinge. This is the notation for the hinge. All right, it is supported by the hinge. So hinge will exert two reactions, one horizontal, one vertical. Horizontal reaction is normally referred as H. Vertical reaction is referred at V, right? So it is a horizontal reaction at A. This is vertical reaction at A. Now this is same thing is there. It is shown in the line diagram. It is a body which is supported by hinge at A. So hinge support at A is exerting two reactions, horizontal and vertical, H and V. I've shown a body which is inclined, but it is again hinged at A. This is also the notation for the hinge support. This is also the notation for the hinge support. A big dot is marked. So that also is indicative that it indicates that it is a hinge support. So hinge exerts two reactions. So in short, you'll remember that hinge support exerts two reactions, one horizontal, one vertical, or we can say that two reactions are mutually perpendicular. Direction, the reactions are arbitrarily assumed. So we cannot say that reaction, horizontal reaction will be to the right or to the left, or vertical reaction will be upward or it will be down. Next, we come to the roller support. Now, roller support. As you can see, these are some of the notations of the roller support. These are some of the notations of the roller support in the system. It looks us like this. Now here you are shown a body which is supported by a roller on the left hand side. So roller allows the body to move along the plane. Roller allows the body to slide along the plane, but it provides normal reaction. In this case, the roller is resting on horizontal plane, so normal reaction or the reaction exerted by the roller will be vertical. On this side, you can see that you have a plane which is inclined at angle theta with the horizontal. Reaction exerted, there is a roller which is resting on this plane. So roller will exert normal reaction. Roller will exert normal reaction. So normal means normal to the plane. Normal means what? Normal to the plane. So you can see that these are some of the notations of the roller support, and we should remember that roller exerts one reaction which is perpendicular to the plane on which roller is resting. As you can see here, it's normal to the plane. Plane is horizontal, reaction is vertical. Here plane is inclined, so even reaction, normal reaction will also be inclined. Now here you can see slight geometry part. You can study that. You can see that plane is making angle theta with horizontal. Reaction is normal, so this angle is 90. So this angle is 90 minus theta. All right. Next, we come to fixed support or built-in support. This is the highest level of the support in coplanar forces. Fixed support means the body is fixed to the wall or to the system in such a way that body is not allowed to rotate. Body fixed support does not allow the body to rotate, and at the same time it does not allow the body to move in horizontal as well as in vertical direction. So fixed support will exert three reactions: one horizontal, one vertical, and third is in the form of movement, since rotation is also not allowed. Here the body is shown with the thickness. So this support is fixed support. We also call it as built-in support. This is the same thing has been shown where the body has been fixed to the wall also. So wall will this fixed support will exert three actions: horizontal, vertical, and third is in the form of movement. Hope you all understand it. So in short, what again I repeat that what you need to remember it. You need to remember that hinge support exerts two reactions, one horizontal and one vertical. Roller support exerts one reaction. Roller support exerts one reaction, which is always perpendicular to the plane on which roller is resting. We should also remember that fixed support exerts three reactions, one horizontal, one vertical, and third one is move in the form of movement. Again, I repeat that direction of the reactions exerted by the hinge, roller, as well as the fixed support are assumed. You cannot be sure that whether what will be the direction of the reactions. Next, we come to free body diagram. Now, this term is very, very important. Free body diagram, that means diagram, in short, what you understand, diagram of the free body. Drawing the free body diagram is the most important part in the solution of the problems of equilibrium, because unless you draw the free body diagram, you do not understand whether it is body is forming a concurrent force system, parallel force system, or general force system. So after we have drawn the free body diagram, then we understand it is a which force system, and accordingly the equilibrium conditions are applied. So we say that drawing free body diagram is the first step towards the solution of the problems of equilibrium. To draw the free body diagram, the body is detached from all the supporting systems, maybe like a string or hinge, roller, fixed support, wall, and then we show all the forces what these supporting systems were exerting. So in short, you will show all active as well as reactive forces. The diagram of the body with all active and reactive forces acting on it is called as free body diagram. Now you will understand some of the examples of free body diagram. Can you see that here you have a beam? Beam means like a bar. In simple words, beam means like a bar which is hinged at A and it is roller supported at B. Can you see that? Now on the right side, we have drawn free body diagram. Here hinge will exert two reactions, one horizontal, one vertical, HA and B. And roller will exert one reaction normal to the plane. The plane on which roller is resting is horizontal. Reaction exerted by the roller will be vertical. Second example, you can see that we have taken a beam whose one end is fixed and other end is free. The fixed support will exert three reactions at A. Can you see that? HA, VA, and AB. Direction of these reactions are arbitrarily assumed. Once we solve the problem, we come to know whether our assumption was right or our assumption was wrong. Now, we take third example. In the third example, I've taken, there is a sphere which is resting on three smooth planes. This is a sphere which is resting on three smooth planes. One is horizontal, another is vertical, third one is inclined also. Now, we need to understand in a plane, in coplanar force system, sphere, cylinder, or wheel, disc, all right, or roller, all these are indicative of the circular body only. Now, if you draw the free body diagram of this sphere, now I have drawn the free body diagram this time. What you need to remember that weight is has been shown at its center of gravity. Now, smooth planes exert normal reaction and that too towards the body. Now, this plane is horizontal. The sphere is resting on the horizontal smooth plane at A. So reaction exerted will be normal to the plane. You can see that normal to the plane R. Here it is resting on vertical plane, so normal reaction will be towards the body, that is R. Here plane is inclined, making angle theta with horizontal, reaction RC will be normal to the plane. At this stage, we should understand that reactions exerted by the smooth planes on the circular body will be passing through the center. Why the reactions will pass through the center? Because these reactions are nothing but normal to tangent of the circle. If you draw a normal to the tangent of a circle, it will always pass through center. This property makes us to understand that smooth plane reactions will exerted at A, B, and C. All RA, RB, RC, all will be towards the body, and all the three reactions will be passing through the center of the sphere. Okay. Now we take the fourth example. In this example, I've taken a beam which is hinged at A and it is supported by a string at B. And this string BD is connected to the wall at D. Now we need to draw the free body diagram. First, we should understand that if you say string, we have to draw the FBD of string, we have to draw FBD of the beam. If I draw FBD of the string, we should understand that string, wire, cable, rope are the components. You can pull them, but you cannot compress them. So these are the components which can be subjected to only pulling force. Pulling force means what? Tensile force. So string, wire, cable, rope will always be subjected to tensile force. So can you see that here? It's subjected to pulling force. You can see tension T, which is away from B outward. This is also tension T away from D, right? So it is a pulling tension is means the string is under tension. It is the forces will act away from the string, right? You can see there it is acting away from D. It is acting away from the body at B. Now, when we draw the free body diagram of the beam, which is supported by the string, now you can see that at A there was a hinge, so there will be two reactions, H and B. Weight is shown as it is. At B, where it was supported by the string, you will show tension in the string. You will show tension in the string. Tension in the string means it is away force. Away force means it is away from the beam in the direction of the string. So you will show tension in the string, which will be shown away from the string, and it will be in the direction of the string. Normally, it is found that we don't need the free body diagram. While solving the problems of equilibrium, we don't need FBD of string, right? We draw the FBD of the body which is being supported by the string. Next example. You have a rod which is resting inside a sphere. You have a rod which is resting inside a sphere. This rod is resting inside a hollow sphere. You have to draw free body diagram of the rod. First, you have to draw the tangent at A and B to the circle. We have drawn the tangent at A, we have drawn tangent at B to the circle, and reaction exerted by the circular curved surface will be normal to tangent. So reaction RA will be normal to tangent at A, reaction R will be normal to tangent at B. So RA and RB will be definitely passing through the center of the sphere, right? So in this type of situation, when there is a rod which is resting inside the hollow sphere, the reaction exerted by the end of the rod will be normal to the tangents as shown in this diagram. RA and RB are normal to tangents, and they will be definitely passing through the center. Next example is we have a bar whose one end is resting on the smooth wall. In between, it is supported by a peg or a nail. In between, it is supported by a peg or the nail. You want to draw the free body diagram of this. Can you see that? If there is a smooth wall, it will exert normal reaction. We have shown RA. Weight is acting vertically downward, and the peg or nail will also exert normal reaction. That too towards the body. Peg or nail will also exert normal reaction, that too towards the body. That means towards the bar. So reaction RB is perpendicular to the bar, and that too towards the bar. Now we come to the next example where we have a bar or beam which is resting on the smooth horizontal floor, and it is supported by the edge. Edge means it is also called as fulcrum. What is called as fulcrum? Now you can see that on the right side, you can see the free body diagrams. The bar is supported on horizontal floor, which will exert normal action. Smooth floor will exert normal reaction, and this edge, which is junction of horizontal and vertical plane, will also exert normal reaction towards the body. We should remember that the edge or the fulcrum, which is junction of horizontal vertical plane, if the bar is in its contact, the edge or this fulcrum will exert normal reaction towards the body. As you can see that RB is towards the bar and it is perpendicular to the bar. So these are the some of the examples of free body diagram which we need to remember, which we need to all these examples make us to understand what with the free body diagram is to be drawn when we are solving any problem of equilibrium. Now, some of the important points which I have highlighted here, we have already discussed, but once again, I'll just touch upon that because they have their own importance. First, I told you that already discussed that direction of the reactions at hinge, roller, and fixed support are arbitrarily assumed. I mean, directions are assumed. After solving the problem, you will come to know the exact direction of the reactions of hinge, roller. Next is that smooth planes exert normal reaction towards the body. In case of the example of sphere, we understood it. Next, element like string, wire, cable, thread, rope, etc. always subjected to tensile force, never compressive. You should remember it. For solving the problems of statics, the string, wire, cable, rope, thread, etc. are always subjected to tensile force, never compressive. And tension means what is away from the body. As we took it tension on the free body diagram of the beam, where it was supported by the string, tension was taken away from the beam, and that too in the direction of the string. And compression means what? Towards the body or towards the joint. For solving the problems of equilibrium, we don't need FBD of rope, cable, wire, etc. is never drawn. Now, similarly, for solving the problems of equilibrium, we don't need the free body diagram of the wall, floor, ceiling, hinge roller, hinge support, roller support, or fixed support is never required. We always need the free body diagram of the body which is being supported by these supporting systems. Pegged nails or fulcrum exert normal reaction, that too towards the body. Next, in case of the frictionless or smooth pulley, if you have a string or wire or cable or rope which is taken around a frictionless or the smooth pulley, tension in the rope will be equal. Tension in the rope will be equal, and it will be tension will in the rope will always be away from the pulley. It will be always away from the pulley. Point number 8 is if the plane is making angle theta with the horizontal, force or reaction normal to the plane will make angle theta with the vertical. It is a students purely a geometrical note which I'll be discussing while solving the problems. Also, that reaction between the two bodies in contact will always be equal opposite. We always understand it that if the two bodies are in contact and we are separating them out, there will be common reaction which will come into consideration, which will be equal and opposite. This point also will be understanding when we are solving the problems in my subsequent slides. Now, one of the most important theorems which we use it while solving the problems of equilibrium is Lami's theorem. Lami's theorem, students, is one of the most important theorem what we use it for solving the problems of equilibrium. What Lami's theorem state that? Lami's theorem state that if three forces acting at a point are in equilibrium, if three forces acting at a point are in equilibrium, I mean, or you can say that if three concurrent forces are in equilibrium, then ratio of any of the forces to the sine of the angle between the other two is constant. That means P upon sine alpha, Q upon sine beta, R upon sine gamma. You can see that here it is listed. I repeat again, Lami's theorem states that, Lami's theorem is also important theorem. Lami's theorem states that if three concurrent forces are in equilibrium, then ratio of any of the forces to the sine of the angle between the other two is constant. Like this is P upon sine alpha, Q upon sine beta, R upon sine alpha. Now this geometrical construction, this and this are drawn to derive this theorem. This theorem is derived using sine rule in a triangle. We have simply extended the line of action of the three forces on the other side. So that alpha, this was alpha. So here this is 180 minus alpha. This angle was beta. This is 180 minus beta. This is gamma. This is 180 minus gamma. As three concurrent forces are in equilibrium, they can be represented by the three adjacent sides of a triangle taken in order based on law of polygon. And then we simply apply sine rule. P upon sine 180 minus alpha, Q upon sine 180 minus beta, R upon sine. And then it comes out to be the derivation of Lami's theorem. Now, most important thing about the Lami's theorem is that as it is the favorite theorem of the students, we should also know when Lami's theorem is not applicable, or what are the limitations, when we should use Lami's theorem, when we should not use Lami's theorem. First thing is that you should understand that Lami's theorem is not applicable for parallel and general force systems. Can you see that? It's not applicable for parallel. It is applicable only for concurrent force system, and that too only when three concurrent forces are not in equilibrium. That means, again I repeat, this is not applicable for parallel force system, not applicable for general force system, applicable for only concurrent force system, and that too only when three concurrent forces are in equilibrium. It is not applicable for less than three. It is not applicable for more than three. Lami's theorem does not give direction of unknown forces, whether this P is towards the body or away from the body. Lami's theorem does not talk about that. Lami's theorem will give you only value of P. So at times when you are assuming the direction of P, Q or R, then you should not assume you solve the problem by using Lami's theorem. The last limitation, which says that none of the angles should exceed more 180 degree. Why none of the angles should be exceeding 180 degree? Because Lami's theorem derivation is based on sine rule in a triangle. If alpha, beta, gamma, any of the angle between the two forces exceeds 180 degree, then you cannot apply Lami's theorem. So all these limitations and all this is its usefulness of this theorem, or what are the limitations, all these things we'll understand while we are solving the problems of concurrent force system. Now we'll discuss some more theory part of the chapter. As I'm discussing the theory of this chapter at length in the beginning itself, because the theory of equilibrium has to be discussed at length before we start solving the sum, because there are many important points which you'll come across in the problem. So if you have already discussed once, so when we are solving the problem, it becomes easy for us to understand. Now, next we are talking about, these are all you can say exceptional type of situations what we come across when we are solving the problems. Two force body. What do you mean by two force body? In simple words, a body which is acted upon by the two forces called as two force body. You need to understand when the two force body will be in equilibrium and when it will not be in equilibrium. Two force body will be in equilibrium when the two forces are equal in magnitude, opposite in direction, and acting along the same line of action. Can you see that here? I've shown two examples. This example, it is a L-shaped body. There are 2 points A and B. 10 kilonewton is applied horizontally at A. 5 kilonewton is applied at B. These two forces will not keep this body in equilibrium. These two forces will not keep this body in equilibrium because they are neither equal in magnitude, they are not acting opposite direction. So it is, we can say this body will not be in equilibrium. Whereas in the second example, you can see that this two force body will be in equilibrium because two forces acting at A and B are of 10 kilonewton. Oh, by mistake, it is 5 kilonewton strength. It has to be same. It is 10 kilonewton here. So this also has to be 10 kilonewton. There is a minor correction in that. So two forces, as the definition says, they have to be equal in magnitude, opposite direction, acting along the same line of action. So this is just by mistake. It has been put to 5 kilonewton. You just have to understand it has to be 10 kilonewton. So then this two force body will be in equilibrium. 10 kilonewton here, 10 kilonewton here, 10 kilonewton at A, 10 kilonewton at B will be keeping the body in equilibrium. At the two forces will be equal in magnitude, opposite direction, acting along the same line of action. So this is a minor correction. Please note it. This is not 5 kilonewton, but it is 10 kilonewton. Then only these two 10 kilonewton forces acting at A and B will keep the body in equilibrium. So do remember that what I have written it here, two force body will be in equilibrium. The two forces are equal in magnitude, opposite direction, and acting along the same line of action. Now we talk about three force body. Similarly, a body which is acted upon by three forces is called as three force body. Three forces will keep the body in equilibrium when they form either the concurrent force system or they form parallel force system. Do remember that three force body will not be in equilibrium. Three force body cannot be a general force system, right? We have to remember that either if they are parallel, three parallel forces, they can keep the body in equilibrium. If they are not parallel, they have to be concurrent. So this conclusion helps us in solving many problems, right? I will justify this statement. I'm taking a body which is acted upon by three forces, F1 acting at A, F2 acting at B, and F3 acting at C. Now, these three forces are non-parallel. So what will I do that? I'll pick up two forces, F1 and F2. I'll extend their line of action and I'll make them to act at point T. So F1 is shifted along its line of action using what principle? Principle of transmissibility. I have used it. We understood it in the resultant chapter. Already you must have watched the video lectures of resultant chapter. Similarly, force F2 shifted to act at point T. So now F1 and F2 are concurrent at D. Forces F1 and F2 are concurrent at D. Now the resultant of F1 and F2 will also pass through D. Say ah. Now what has happened? These three forces were F1, F2, F3, so it was three force body. Now I have reduced it to two force body. What are the two forces? R and F3. R and F3 will keep the body in equilibrium only when they are equal in magnitude, opposite in direction, and acting along the same line of action, which indicates that force F3 has to pass through D. That means three known parallel forces, F1, F2, F3 will keep the body in equilibrium when they are concurrent. So at last we conclude that three known parallel forces will keep the body in equilibrium when they are concurrent. So they cannot form a general force system. This is something what we need to remember. Now, friends, as we understood, B means a bar. All right. Now, how the bar is supported, it is called by different names. One is simply supported beam. Simply supported beam, you can see that it is simply supported on the support in such a way that only normal reactions are exerted. Such a support is called as simple support, and the beam which is resting freely over the two supports at the two ends so that only normal reactions are exerted is called as simply supported beam. If you say simply supported beam, it is resting freely over the two supports so that the two end supports will exert only normal reaction. Next, we'll understand other types of the beams. Cantilever beam. What is a cantilever beam? The beam which is fixed at one end and free at the other end is called as fixed beam. Cantilever. Next is propped cantilever. What is a propped cantilever? The beam which is fixed at one end and simply supported at the other end is called as propped cantilever. Next is fixed beam. A beam which is fixed at both ends. You can see that it is fixed at left end and it is fixed at right end. Such a beam is called as fixed beam. Next comes continuous beam. Continuous beam means the beam which is having more than two supports. Can you see that the beam is support? This is one fixed support, simple support, simple support. So it has three supports. Such a beam which is having more than two supports or more than one span. This is one span, this is second span. So we can say any beam which is having more than two supports and having more than one span is called as continuous beam. Next comes overhanging beam. Overhanging beam means the beam in which some part of the beam is overhanging or it is projected beyond the support. Like in this case, you can see that this is a simply supported beam as the two supports are simple supports, but some part of the beam is projected beyond the simple support on left side. So it is overhang on left side. In this side also there is overhang. It is projected beyond the support. We call this simply supported beam with overhang on both the sides. Now we have to understand what will be the sign convention for the equilibrium conditions which we are going to use. If we say sigma fx is equal to 0, in simple words, we can understand that algebraic sum the component of all force in x direction is 0. But if you little bit think over, that means do we not understand that forces towards right should be equated to forces towards left? So if you say sigma fx is equal to 0, that means forces are balanced in x direction. That means force x direction is horizontal. So forces towards right should be equated to forces towards left. That's what I have listed here. Similarly, when we talk about sigma Fy is equal to forces acting upward should be equated to the forces acting downward. When we say sigma Ma is equal to 0, algebraic sum of the moment all force about A is 0, that means what? Its clockwise movement should be equated to anti-clockwise. Clockwise movements are equated to anti-clockwise movement. As you can see that here, this is a clockwise movement, this is anti-clockwise. So clockwise movements can be written on one side, anti-clockwise movements can be written on other side. There is no, you can put anything on left side, anything on right side. You can write anti-clockwise movements on left side, so right side will be clockwise movement. If you are writing on the left side clockwise movement, right side will be anti-clockwise. This is what will be the change of sign convention, what will be adopting. It is important for all students to understand that don't use resultant sign convention. You can use the resultant sign convention. What was the resultant sign convention for sigma Fx? Forces towards right were taken positive, towards left were taken negative. You can use that sign convention, but that will take more time of yours in the examination. So it is better way of understanding of equilibrium condition is that sigma Fx equal to 0. When I say that, that means no negative, no positive. Forces of one nature one side or opposite nature on other side. Similarly, for sigma Fi, upward forces will be on one side, downward on other side. For sigma M, clockwise movements on one side, anti-clockwise movements will be taken on other side. All right, friends, now we are ready to start with the problems of equilibrium. I have written the heading here. You can see that what heading I have written, equilibrium of concurrent force system. This is about type 1 problems. Students, this lecture, this topic is the most important topic of statics, having maximum weightage. And so I'll be covering this topic, this chapter in 4 parts. Right now, I've taken part 1, as you can see in the on the screen. It is part 1. In this part, I have covered major part of the theory of this chapter is already covered. All right, now it will be only problems. We'll be covering more than 50 problems. We'll be covering in my 4 lectures on this chapter. All right. So the first type of the problems are type 1, equilibrium of concurrent force system. We already discussed what are the equilibrium conditions for concurrent force system. Sigma Fx is equal to 0, sigma Fy is equal to 0, and that's it. So there will be 2 equilibrium conditions. If there are 2 equilibrium conditions, that means there will be 2 simultaneous equations and there will be 2 unknowns will be there on the equilibrium in the problem. First problem, all these problems have been taken from my book. All right, and there are more solved problems given in the book. There are many unsolved problems are also there. Multiple choice questions are also there. Theory also has been discussed in the lecture also. There will be all these theories also given in the book also in an elaborative manner. Solved problems, I have covered maximum number of problems. All types of problems will be covered in my video lectures, but still there will be many more problems solved as well as also unsolved in the book. So do refer my book. All right, do watch video lectures. There won't be any tuitions or anything required. If you are referring my book and you are watching my video lectures, you can aim for full marks. 100 on 100 you can aim for. That is what I can assure you. All right, my first problem. Determine the tension in the cables AB and BC for the equilibrium of 30 kg block. That is, this problem has been taken from Mumbai University examination 2015 for 4 marks. Now this is one cable, another cable, and a weight or a block of 30 kg is attached. In this type of problems, sorry, when number of strings are knotted together, when number of strings, wires, cables, etc. are knotted or connected together, and system is supported at the ends from on the wall or the ceiling. To solve this problem or to find the forces in the cable or tension in the cables or wires, we draw free body diagram of intermediate point or intermediate support, right? Or intermediate joint. So what is intermediate joint here? Joint P. So we will be drawing free body diagram of joint B. which if you are drawing FBD of a joint, it will always be example of concurrent force system. So let's draw free body diagram of joint B. What are the forces which will act at joint B? One will be this weight, which is acting vertically down. So 30 into 9.81 mg. This is m is mass 30 multiplied by g. This is 294.3. This angle is 40. Tension in this cable will be away from it. Away from where? Away from joint B. Right? We always already understood that tension in the cables will always be away from the body. Right? Tension is, so I'm assuming the tension in cable AB is TAB. Tension in the cable BC is TBC. Now, as it is a concurrent force system at joint B, you will be applying sigma fx and sigma fy is equal to 0. So we will resolve the force anywhere along its line of action. So which forces need resolution? The forces which are inclined to x or y axis. Now TBC, is it making 40 degree? So I can write 40 here. So adjacent component is cos, TBC cos 40, TBC sin 40. Similarly, this tension in cable AB, TAB is making 30 with horizontal. So I wrote 30 with horizontal. So adjacent component is TAB cos 30 to the left, and other component TAB sin 30 is vertically up. All right. So we know from the resultant of coplanar forces chapter that in case of concurrent force system, forces can be resolved anywhere along its line of action, since we do not apply any movement equilibrium condition in this type of systems. Now we have resolved the forces. Now we'll write sigma fx equal to 0. Sigma fx is equal to 0 means forces towards right should be written on one side, forces towards left should be written on other side. So I'm writing TBC cos 40 is to the right equal to TAB cos 30. That's what is the real meaning of sigma fx equal to 0. Forces towards right are equated to forces towards left. Now sigma fy is equal to sigma fy is equal to 0 means upward forces on one side, downward force on the other side. What are the upward forces? TAB sin 30, it is upward, plus TBC sin 40, it is upward, equal to 294. So we got the two simultaneous equations. Now sigma fx equal to 0, from where we are at forces towards right equal to forces towards left. Sigma fy is equal to 0, upward forces are equated to downward forces. So we got two simultaneous equations, 1 and 2. Just solve them using your calculator, you'll get the tension in the two cables. TAB comes out to be 239.92. TBC comes out to be 271.2. Well, students, this problem we have solved in a fundamental manner. We have solved it in a fundamental manner means I have used the equilibrium condition sigma fx equal to 0 and sigma fy is equal to 0. But this problem can be better solved using Lami's theorem, which we'll understand in the subsequent examples. Important part I have already discussed in the problems where number of strings are connected, knotted together. At the end, the system is supported on the wall and ceiling. We get the forces in the strings, wires, or cables by drawing free body diagram of intermediate joints. This will be apparent or it is understood even in the next problem also. Now, we come to the problem number 2. We read it. A 30 kg pipe is supported at A by a system of 5 cords. There are 5 cords in the system. Find the force in each cord for the equilibrium. Now, this is one cord BC, BD, AB, AE, and this. Actually, this is not a cord. This is just a weight is suspended. So basically, you need to find the tension in the cord BC, tension in the cord BD, tension in the cord AB, tension in the cord A. And this tension in the cord is already known to you. This is 30 kg only. We have to convert it into weight. All right. Now, question arises here. As per our understanding, it is a problem in which number of strings are connected together and the entire system is in equilibrium by suspended or connected to the wall and the ceiling. Now, here there are two intermediate points. To find the tension in each cord or tension in each cable, we have to draw free body diagram of intermediate points. What are the intermediate points here? Joints A and B. So this problem has to be solved by drawing free body diagram of joint A and joint B, right? Now, if I draw free body diagram of joint B, there will be 3 unknowns. This is also a point which is always important. See, if I draw FBD of joint B, you'll have tension in BC away from B, tension in BD away from B, tension in AB, away from. So three unknowns will be there. Whereas if I draw FBD of joint A, there will be two unknowns. What are the two unknowns? This 30 kg, this tension in this string is known, tension in AE and tension in AB. So you should start solving from the free body diagram of a joint, which will give you the result. There is no rule whether you have to start from FBD of joint B or you have to start from FBD of joint A. So ideally we should start from FBD of joint A, as you can see over here. I have started from free body diagram of joint A. If I see that at A, weight will act weight, which is 30 kg pipe weight, which will act vertically down, 30 into 9.8 to 294.3. On this side, there is a cord or string, namely A. So tension in cable A, it will be away from A in the direction of cable. On this side, tension in the cable AB will be away from joint A in the direction of cable. All right. Now, it is a concurrent force system. There are two unknowns. You can apply the two equilibrium conditions and you are surely going to get both. Now, TAB, tension in AB, this is 60-degree angle. It is given here, right? I wrote it here. I resolved the tension. Again, you can resolve the tension in cable AB anywhere. So anywhere along the line of action, I have resolved it. So adjacent component is cos, other component is sine. And direction of the component is nothing but projection of the arrow of the force. So TAB is like this. So TAB cos 60 will be to the left, TAB sine 60 will be upward. Now, students, we need to apply the equilibrium conditions, right? Sigma, you can start. Another thing that when you are drawing the free body diagram of a joint and it is concurrent force system, you can apply the equilibrium conditions in any sequence. You can apply the equilibrium condition. There is no need that you have to always start with sigma fx equal to 0. You can start with sigma fy is equal to 0 also. Whatever is convenient, whatever gets you the result fast, you can start with that. Like in this problem, with this FBD, I have started with sigma fy is equal to 0. Why? Why I started? Because sigma fy is equal to 0 means upward is equal to downward. There is only one upward force, TAB sine 60. There is only one force downward, 294.3. So our TAB sine 60 is 294.3. So you get the value of TAB. Is that all understood this to everybody? We did not start with sigma fx equal to 0 because if we start with sigma fx equal to 0, I'll get a TAB cos 60 is equal to TA. But if we apply sigma fy is equal to 0, we could get some unknown. And now I write sigma fx equal to 0, so TA is equal to TAB cos 60. Substitute the value of TAB, you get the value of TA. So you got the tension in two cords or two strings. Now, when I go to FBD of joint B, tension in string AB is already known to me. Tension in the string AB is already known to me from FBD of joint A. So this joint is now workable. This joint is now workable, or it can be solved. You will get two unknowns without any problem. Now you can see that here. You can see that. I've drawn FBD of joint B. This side there was a cable. So tension in that cable is TBC. This side there was cable AB. So tension in the cable AB will be away from joint B2 in the direction of cable. Your TAB we have taken. Angle 60 degree which was given to you. Yes. Tension in the cable BD is TBD. It is making angle theta with the horizontal. Can you see that? Here I formed a right angle triangle. This right angle triangle is nothing but 3, 4, 5 right angle triangle. So from here, what do you understand? Tan theta is 3 by 4. Cos theta is base upon hypotenuse 4 by 5. Sin theta is opposite upon hypotenuse 3 by 5. Which you can see in the previous slide also, it has been marked that. It is marked in the just a minute, there is slight issue in the Start the slide which is in between. Right. Go back. Yeah. Now you can see that here. Now I've just taken the previous slide. You can see that here this is 3 4. So I was showing that tan theta is 3 by 4, and cos theta will be then 4 by 5.8. Sin theta is 0.6. Just a minute, hold for a minute. There's little problem in changing the slide. Change the slide to the next one. Well, now when we draw FBD of joint B, so you can see that here tension the cable AB was already known to us. Tension the cable AB was already known to us. So we have resolved tension cable BD as TBD cos theta, TBD sin theta. Adjacent is cos, other is sin. Here TAB is adjacent is cos, TAB cos, and TAB sin. We write sigma fx equal to 0. So what is it? TBD cos theta plus TAB cos 60. They are to the right, and sigma fx. So, but to begin with, we have not taken sigma fx. We have taken sigma f5. Sigma f5 is what? TBD sin theta is up is equal to TAB sin 60. All right. Now TAB value is already known to me. Here rather I have substituted the value of TAB sin 60, that is 294.3. So you get TBD. Then sigma fx equal to 0 gives you TBC is equal to TBD cos theta plus TAB cos 60. So TBD and TAB values are substituted, you get the tension in. So this way, tension in all the 4 chords are arrived at. Now here, students, I have listed equilibrium conditions sigma fx and sigma fi is equal to 0 may be applied in any sequence. What does it mean? You can start with sigma fx equal to 0, or you can start with sigma fy is equal to 0. In the problem already discussed, we need to start with the free body diagram of joint A, since there are 2 unknowns on that FBD. Free body diagram of joint B should be drawn later, because after solving joint A, then joint A becomes workable. Also, again, I have listed one more thing, that this problem can be solved by using Lami's theorem also, which we will be showing it in the next problem. Next problem, I'll be solving it by equilibrium conditions as well as using Lami's theorem. Once again, slight problem is there in the changing the slide. Just hold for a minute. Now, next problem. This is the third problem I'm taking. There is a cylinder of 1500 Newton weight is resting in an unsymmetrical smooth groove as shown in figure. Determine the reaction at points of contact. So this is your cylinder. You have to consider that it is a circular body. All right. This problem has been taken from a university examination of May 2014. That is 4 marks. Now we need to see, we do not draw FBD or smooth planes. We will draw FBD of the body which is being supported by this smooth plane. So I'll draw FBD of this cylinder. I'll draw FBD of this cylinder. If I draw FBD of this cylinder, weight will definitely act vertically down at the center. This plane, this is smooth plane. So smooth plane will exert normal reaction towards the body. This is smooth plane at V, which will also exert normal reaction towards the body. Now, so here this reaction RA is towards the body. Reaction RB will also be towards the body. Next question arises that how to arrive at their angles. See, we understand that these reactions will pass through center of the cylinder. RA and RB both will pass through the center of the cylinder. But what angle it will make with horizontal or reaction RA or reaction RB, what angle it will make with horizontal, for that I have just drawn some important geometrical note. Can you see that here in this geometrical note? This is one plane I have taken which is making angle theta with horizontal. This is the plane which is making angle theta with the horizontal. Reaction normal to the plane. You can see this is angle theta, this is 90, this is 90 minus theta, this is theta. So what we can conclude, this plane is making angle theta with horizontal. Reaction or force normal to the plane will make angle theta with vertical. Similarly, on this side, this plane is making angle theta with horizontal. Reaction normal to the plane will make angle theta with vertical. Theta 90, this is 90 theta, this is theta. This is what I have listed. This is what I have listed. If the plane is making angle theta with the horizontal, as shown in this diagram as well as in this diagram, any force or reaction normal to the plane will make angle theta with the vertical as shown. Now you can just see that in this side. So this plane is making 45 degree with the horizontal. This plane is making 45 degree with the horizontal. So reaction RA, which is normal to the plane, will make 45 degree with the vertical. And of course, this reaction will pass through the center of the cylinder. Similarly, on this side, this plane is making 60 degree. Reaction normal to the plane will be definitely towards the body. Reaction RA and RB will be towards the body. And reaction will be passing through the center of the cylinder. All right. This plane is making 60 degree with the horizontal. Reaction normal to the plane will make 60 degree with the vertical. Now you can see that I've just drawn a separate diagram. Weight 1500 vertically down. This reaction RA which makes 45 degree the vertical. I have resolved it on the tail side anywhere. So this is making 45 degree the vertical. RA cos 45, RA sin 45. Adjacent is cos, other is sin. This reaction RB which is towards C, it makes 60 degree with vertical, you can see here. So 60 degree vertical, I have written it over here at 60 with vertical, or you can say alternate angle. This angle and this angle are alternate. Similarly, this angle and this angle are also alternate. But you can remember it that alternate angles are equal, or you can remember it that RA is making 45 degree the vertical. So either you mark it here or you mark it here. Similarly, reaction RB is making 60 degree with the vertical. So you mark it here or here. Now we have resolved it. This is RA cos 45, RA sin. Adjacent is cos, other is sin. Similarly, RB cos 60 and RB sin 60. We apply sigma fx equal to 0. Forces towards right is RA sin 45 is equal to RB sin 60. Sigma fy is equal to 0. Upward forces are equal to downward forces. Upward forces RA cos 45 plus RB cos 60 is equal to 1005. If you solve these two equations or do two simultaneous equations, you will get the value of RA and the most important thing what we have learned in this problem is that if this is a geometrical note, if the plane is making angle theta with the horizontal, any force or reaction normal to the plane will make angle theta with the vertical. Now you can see this. You can see we solved equation number 1 and 2 given on the previous page. RA is 1344.9 making 45 degree with the horizontal. You can give the angle with horizontal or vertical, but normal practice to give the angle of the reactions or unknowns with the horizontal. RB will make 30 degree. We understood it from the geometry, 60 degree with the vertical, so it will make 30 degree with the horizontal. So we have shown it in the answer. Now, same problem now we'll solve by Lami's theorem. For the Lami's theorem, 1500 down, RA is towards the body at 45 degrees vertical or 45 degrees horizontal. RB will make 60 with vertical, that means 30 with horizontal. So we wrote all angles. I wrote this is 90, 90. Now, this is the fit case to apply Lami's theorem. What is the essential condition to apply Lami's theorem? Lami's theorem states that if three concurrent forces are in equilibrium, then Lami's theorem can be applied, but you should make sure that none of the angle is more than 180 degree. You can see that there is no angle between the two forces which is exceeding 180 degree. So all angles between the two forces are less than 180 degree. There is one more condition. What is that? Direction of unknown is not assumed. So RA and RB, we are sure that they are towards the joint as shown in the diagram. RA and RB are not direct, their directions are not assumed. So we now apply Lami's theorem. How we apply Lami's theorem? RA upon sine this angle between the other two, 90 plus 30. RB upon this angle, sine 90 plus 45. 1500 upon this angle, sine 45 plus 60. So RA upon sine 120, RB upon sine 135, 1500 upon sine 105. If you solve this equation using your calculator, RA and RB, you'll get the same answer what we got it over here. So at this stage, you'll realize that use of Lami's theorem is quick, fast, and it is liked by the student, but we should always make sure that whenever it is applicable, then only we should apply it. If it is not applicable, as we told you that it is not applicable when we have more than three forces. All right. And direction of unknown should be known. No angle should exceed 180 degrees. Otherwise, it is not. In spite of so many limitations, Lami's theorem is a very useful theorem. We will solve it. We will use it as and when it is applicable. All right. So in subsequent problems, I'll always use Lami's theorem as and when it is applicable. Now we move to the fourth problem on the type 1, that is equilibrium of concurrent force system. So far you have seen that we have used the equilibrium condition sigma fx is equal to 0 and sigma fy is equal to 0. You should understand that sigma fx is equal to 0 and sigma fy is equal to 0 is a set of equilibrium condition which does not have any limitation. Its alternate is only Lami's theorem, but Lami's theorem is applicable only in limited examples. It is not applicable in all problems, but sigma fx is equal to 0 and sigma fy is equal to 0. This set of equilibrium conditions is applicable without any limitation in all problems. All right. Anyway, now we move to the next problem. A cylinder B of diameter 400 mm and weight is 5 kilonewton is held in position as shown in the figure with the help of the cable AB. Find the tension in the cable and reaction developed at the contact. The problem is taken from the Mumbai University examination of December 2018 with 4 marks. Now this is your cylinder is given to you. This cylinder is resting on the inclined plane, which is 45 degrees horizontal. At the center of the cylinder, it is connected to a string or a cable, which is connected to the plane over here. Obviously, as we already understand, we do not draw FBD of planes. FBD of smooth plane is never drawn. FBD of the cable is also not drawn. So obviously, you will be drawing FBD of a circular body, and which is very much likely that it will reduce to a concurrent force system. It will reduce to a concurrent force system. Now, we understand that diameter of this cylinder is 400 mm. So its radius is going to be 200 mm. Once again, slight problem in just have a little problem changing slide 1 minute. All right. Now we have drawn FBD of this cylinder. From B, I have dropped the perpendicular on the plane so that ABC is a right angle triangle. First, I am finding angle theta. In right angle triangle ABC, what will be tan theta? BC upon AC. BC is 200, radius of the cylinder, and AB is given, AC is given to me as 350. So we got theta. So we understood that cable AB is making angle theta with the plane. This angle is 45 degree. How do you understand this angle is 45 degree? This is 45. So if you draw a dotted line through A, this angle will be 45, and theta plus alpha will be 45. Theta we have already found, so alpha is 45 minus theta. Alpha is what? 45 minus theta. This you arrive at 15 points. Slight printing error is left out. This is 45 minus theta. All right, I hope you can understand. It is 15.25. Now we'll draw free body diagram of the cylinder. Now we'll draw FBD of the cylinder. If you draw FBD of cylinder, what are the forces which will act on it? Weight will act vertically down. This plane is making 45 degree the horizontal. Reaction RC, normal to the plane, will be towards the body. Reaction RC will be towards the body. It will make 45 degree with the vertical. We have marked it at the center of the sphere. Tension T in the cable AB will be away. It will be making angle alpha with the horizontal. I hope you can see that. Cable AB is making angle alpha with the horizontal, so we have marked it. You want to solve this problem by Lami's theorem. First, you see that only three forces are acting on this cylinder. This will keep the body in equilibrium, but there is a problem. Direction of T is fixed. It is away from B as it is marked. RC is towards the body. All right. Next question comes what? Can we apply Lami's theorem? Yes, but there is a slight problem. What is, if you want to apply Lami's theorem, none of the angles should be more than 180 degree. But you can see that here, this angle on this side, is it becoming more than 180 degree or not? This angle is between 5 kilonewton and RC. Will it be more than 180 degree or not? What will be that angle? 180 plus 45, right? 225. So just to overcome that, tension T is shifted on other side. To overcome that, tension T is shifted on the other side using principle of transmissibility. We have shifted with the maintaining the line of action. It is angle alpha with the horizontal. We shifted it on other side. You can see that direction of the force is not changed. Line of action is not changed. Only it is shifted on other side. It is now we can apply Lami's theorem. When you apply Lami's theorem, one more thing what you can always check it that all forces, when you are applying the Lami's theorem, all forces will be towards the point of concurrence. All forces will be away from the point of concurrence. Now in this case, force 5 kilonewton, RC and T all are acting towards the point of concurrence. Now this angle 90, this is 45 degree with vertical, so 45 degree with horizontal also. This angle alpha is 15.25 degree. This is with the horizontal. All right. So with vertical, it is 90 minus alpha we have marked. Now you can apply Lami's theorem. RC upon this angle sine 90 plus alpha, 90 plus 15.25. Then T upon this angle sine 90 plus 45, and 5 upon this angle sine 45 plus 74.75. So further you simplify RC upon sine 105.25, T upon sine 135, 5 upon sine 119.75. So RC comes out to be 5.5 by 6, which is at 45 degree with horizontal. We got it 45 degree with vertical or 45 degree with horizontal. And tension T is 4.072 kilonewton. Hope this is all understood to everybody. Now in this part, we have covered 4 problems. We covered it. All right. Now we will be covering more problems in the subsequent lecture of this. Thank you.